Hi everyone, this is a work in the 3D vision array that aims to remove the smeared points in the point cloud from the depth sensor, collaborated with Dr. Daniel Morris. You can find our paper, code, and dataset by scanning this QR code in the top right. Okay, let's start our content. There has been significant progress in improving the accuracy and quality of consumer-level depth sensors. Like the state-of-the-art depth sensor, Microsoft Edge Connect, we try to mitigate the systematic error by using higher modulation frequencies, along with the depth invalidation techniques. However, using this sensor still gets invalid points, especially around the object edges. As you can see in the red circle, when we're using this consumer depth sensor, we can find lots of invalid points. The red graph is the colored point cloud converted from depth map using provided intrinsic metric. This kind of invalid points happens in a lot of things. We call such points smeared points, which often interpolate between objects or cross-depth continuities in contrast to other outliers or random noise. Our primary goal in this paper is to eliminate the smeared points without harming other depth points, especially valid boundary details. Before talking about our methods, we first analyze the reason behind it, which is primarily caused by the multi-phase reflection. The sender in the consumer-level depth sensor emits a beam to the adjacent objects existing with depth discontinuities. However, the receiver can get two or more infrared signal reflections back, one from the foreground object and one from the background. These multiple returns can result in a variety of artifacts and typically are interpolated between the foreground and background object. Compared to the common depth random noise, which has a small bias, large variance, and low dependence on 3D shapes. In contrast, the smeared points caused by the multi-phase reflection depend strongly on 3D scenes, with one-sided distribution at object boundaries. Okay, let's talk about the related work. Obtaining the noise-free measurements has always received significant attention. Before the rise of data-driven techniques, the handcrafted filters were designed to alleviate noise by referencing the neighboring pixels, such as median filter, Gaussian filter, and Barrettray filter. As for the related time-of-flight multi-phase interference problems, the multiple different modulation frequencies measurements of the same scene are often required to be collected to improve depth quality. Different with these methods, our method requires only a single frequency depth map for each scene. Besides, the deep learning technique were widely adopted. The DeepTop and RADU in CPR 2022 heavily rely on synthetic datasets generated by a physically based renderer that use bidirectional ray tracing, which is much more time-consuming to render a realistic depth. So there is a gap between the real and synthetic datasets. Moreover, current self-supervised methods require a set of multiple sensors placed in the carefully pre-computed different positions, or need to build some noise models by assuming the noises for some random distribution around normal points, which always leads to the low availability when processing real scenes. Contrast to these methods, our method operates in a self-annotated manner, directly on real scene data without relying on complex scene formation models or specific noise models or synthetic datasets. In our methods, we do not rely on any ground truth or synthetic datasets. We just need to randomly move or lock a handheld depth sensor, and then our method can fuse multiple waypoints to automatically annotate the partial smeared points. As you can see, the smeared points in the red color from valid points in the green color, and left uncertain points in the blue color. Since these smeared points often have large errors, our approach is to identify them for removal rather than collect their depths. So we choose to train a segmentation network only using the partial annotation results for smeared and valid points. Finally, our method can classify pixels in a single frame as smeared or valid. Concretely, our methods consist of two distinct components, a multi-frame pixel annotator and a single-frame pixel detector. In the multi-frame annotated section, we estimate the points to align consecutive frames. Then for each pair of consecutive frames, our carefully designed geometric consistency and evidences is used to annotate the smeared and valid pixels with left points unknown. Then with each pair of annotation results unit and fused, we can use the self-annotated labels in the single frame detector section to get a unit-based classifier training to identify smeared points in each frame. We also found using the omega map based on the normal vector and point wheel direction angle can help to detect the smeared points. Our most important novelty in this paper is to build two geometric evidence, the multi-wheel annotation for the valid points and the space carving annotation for the smeared points. In the multi-wheel annotation for the valid points evidence, if the same point or position is viewed by multiple different viewing directions, then such points are more believed to be valid points. But if the wheel points are in the same direction or small in distance, then the smeared pixels can also coincide together. To avoid it, we use the X theta as a confidence measure. As for the space carving annotation for the smeared points, there are two typical cases, the see-through behind and see-through empty cases. In both cases, a point is to be a smeared point if another wheel point can see through it. In the first case, the figure B, a ray gamma B in the red color from camera at location B passes through a point I observed from the location A and measures a point behind I. And then we conclude the point I is a smeared point. In the second case, the figure C, a point J observed by the camera at location A are also supposed to be visible to the wheel point B. However, there is no any measurement along the ray gamma B, either closer or farther than the point J. And then we just call such points are more believed to be smeared points. Our geometric evidence is concrete from our experiments in the red plot. However, almost 85% of points in our dataset are left unlabeled, as shown in the blue color, so it is necessary to train a single frame network to do the eventual smeared points detection. The qualitative results of our final trained UNet is presented here. The smeared points are colored red, while the valid points are colored green. As you can see, our self-annotated UNet can detect the most of smeared points than the statistic filter, even though more valid points are misclassified as the distance increases. Besides, our trained network can also be applied to the classical 3D reconstruction pipeline, and the multiple frames alignment results using the trained network is presented here. From the left to the right, the second column is a line point cloud without any filtering, and the third column is a line point cloud adding a statistic outlier filter. And the last column is using our network as a preprocessor for the load depth map. Thanks for your watching. You can find more details and our ablation studies by scanning the QR code in the top right.